state for a random number generator, it only requires like 6 or 5 words, so it's cheap. While for another one, Muslim twister, you need like 50 words to store the for your, and yes, it will cost your global memory and I think two generator are currently run library. For small simulation, you may want to try this on faster, and for you may want to try Muslim. So I assume you already know some basics about programming, so I want to give you some general guidance on optimization. So know that for CPU, the idea of optimization is to minimize latency. For GPU, the idea is to hide latency by optimizing throughput, which means you need to use a large number of concurrent threads. Algorithms that have increased arithmetic on large datasets will basically generally have better performance. And actually, you need like 10,000 threads just to hide the latency wear on a GPU card. And the second thing is the efficiently access on global memory, which is also very important. You maximize the memory bandwidth when your card. That means in that case you won't have a codeless memory access. What is codeless memory access? For example, let's say a two-dimensional array flows 8 and 32 columns, and way to write access points for a C or C++ programmer, because you know C++ is the row major. You may want to access the array in this way. So for certain thread, for to access the 0 element and the 1 element, let's look at what's the access pattern for code actually on GPU. If you do it this way, then for the first element 0, each thread actually accesses the global memory at the 0, 32 elements, 64 elements. And you know that the cache line size on GPU is about 128 bytes size, which is too slow elements. Running in terms of warps, and a warps of thread is 32. You 32 have all the data in transaction of measure, but in this case, one loads 32 M, but it only has data for one part for thread. So memory, a core access will have this kind of pattern. You want your access pattern for a two-dimensional array in this way. So you put the actually in the column side. It can't behave like a column access. But if you look at the array access pattern, then for the first element 0, for a warp of thread 32, you this number of data for all the threads in the warp in node. So in case you actually minimize the transaction, which is maximize the bandwidth, minimize the total number of bytes actually transferred. Code memory access is for a C or C++ coder. It's necessary to use array of structure. You define a structure, and then you use the array of this structure. But access pattern would be similar to the first one we saw. You of the thread ID and then access the X element of this structure, this is not called. In CUDA, you may want to try something like structure of arrays. You define an array element as a pointer, and you access all elements X for thread. Then this way, the access pattern is colorless. We want to minimize another thing about optimization is you want to minimize the data transfer between the host and the device, because the PCI Express bus is slow, extremely slow compared to the memory bandwidth of the global memory of the CUDA. And in that case, which means you want to keep the data on the device as long as possible. If you do it asynchronously, you want to overlap communication with computation by CUDA stream. Other way is using this zero copy. But zero copy means that you actually map the whole memory address space to the device. So the device can directly access a pointer point to the host memory. It's detail behind the scene. But don't abuse this zero copy, because actually this data still transfer through the PCI bus, which means it's slow. So, for example, I heavily use this reduction on GPU, and so I steal this from CUDA documentation in CUDA toolkit. How the reductions are done, and I think it's a good example to show some general optimization techniques. Let's say we want to calculate the position of this array given this on shared memory, let's say, and we want to calculate the summation of this array. How are we going to do that on CUDA? Let's say we started with every even number of threads, thread 0, thread 2, thread 4, and let's do the summation. So first iteration, we have half number of threads actually do the work, and number is calculated. Summation number is calculated in the 0 thread, 2 thread, second thread, and fourth thread. And then in the iteration, the sum, intermediate sum is calculated in the 0, 4, and 8. And the final summation result will be in the thread number 0. So this, let's look at code. We need to the address for each data in this global iData is looked at this to the block dimension, block ID X and thread ID X, and load this data to global memory into a shared memory as data. This for loop. If it's for loop, the first iteration, every even number of thread TID to the work. Actually, it's summation TI as data for number of elements to the TID plus S element. Then you synchronize, because the thing is across the block of threads. And all the iteration done, the total, the final result of summation is in your thread number 0. So then you output your thread number 0. If you look at code, so what can you do? First, we have if control, which is TID, the modulus of twice the X number. which means there's a divergence in your control flow. We know in GPU in CUDA, the concurrent activation thread is 32. It's a warp thread 32. But you take a modulus of this thread ID, which means that within different thread has a different control path, exact workflow path, which is actually being serialized. So divergence in your control flow, what you can do is that you calculate the index ID for the thread, and if the index is smaller than this thread block dimension, you can execute this command. So within a warp actually enter this if statement, but you can collect the data on the even number. So that's this. There's no control divergence. And a problem with this code, if you the index ID is calculated, is actually using a thread ID TID multiplied by a number, which means the access pattern to the global memory is right. If you provide access pattern, which means if the basically you cut your memory, global memory bandwidth to a half, so it's really wasteful since this application for this reduction is basically memory bound. To actually make our thread sequential, if we the iteration, then for the iteration, we only need half number of the size block dimension divided by 2. It started now for the previous access pattern, we let the 0, 4, 6, 8 thread do the work. How about we just let the first 0 to 7 thread do the work? So we potential that when t is smaller than this 8, we do summation. So now the access pattern will be looks like this. The arrow and element A, the ninth element, and the thread 1 as the element second to the element 10. So if your access pattern is sequential, you will have the max bandwidth. If you remember the loop, we actually start from half number of threads. So wait, when you start iteration, you already use only half number of threads. So to increase the arithmetic intensity, that is how many arithmetic work operation you do with each node. So we actually, when we load the memory from global data to the shell data, we can already add the first iteration. So we actually do the first iteration when we load the data. That's similar with what we do on CPU. We can unroll the loop. We know the warp size on CUDA code. The mean execution unit on CUDA code is 32 threads. So if thread ID is smaller than the 32, there's no need to actually do the for loop and do the if. You can the whole 32 addition and some execution time. Follow the number of ideas. Another optimization, final optimization. You can completely unroll the whole execution. Do not use a for loop because maximum block size is is 512. The maximum number of threads within a block is this number. So actually, on loop, row or the execution. So if you have this code and compare with the initial code, you can read it if you start with this code. So that's the whole loop of optimization we can do on this reduction. Let's see what's the performance for this optimization. So kernel, which is most readable, or basically where you generally start with. And final kernel 6 you have. Okay, 20 times speed up, just with respect to the kernel we read, initial kernel we written. And the most optimization, the most speed up actually comes from the bandwidth, because it's actually for most a lot of scientific applications found on CUDA. The intensity is not that great, and the bandwidth for kernel 6 is about 20 times of the kernel 1. Thus, you have over 20 times speed up for optimization. Our first case study. First, let's describe what is IC model. So, although it's a model, yet it's very important in statistical physics. So, IC model is like this. Let's say for a two-dimensional lattice, we put in a node of each on the node of this lattice. Each spin can take two values, +1 for start, -1 for spin down. Okay, that's it. That is the IC model. So the energy of this model is defined as this. So with interaction, so each spin interacts with the nearest neighbor. So lattice once have 4 nearest neighbors. And even for this simple model, it already has a phase transition. It can describe magnetic phase transition. That's why it's so important. So how are we going to do that on GPU? First, phase decomposition. Monte Carlo gonna say how is Monte Carlo to study this IC model? Basically, Monte Carlo is using random number to generate this configuration. Let's say we start with one spin and try to flip it. Whether we flip it or not depends on this probability given by this W. This probability is, let's determine the energy change before you flip and after, and then run a number and compare with this flipping probability to see whether we flip it or not. So this is Monte Carlo to update the spin configuration, and we can do spatial decompose because it only interacts with the nearest neighbor, and we have 4 nearest neighbors. So we can do a checkbox decomposition. We compose this whole lattice in 2 sublattices. So sublattice black, sublattice white, and we can then update all things on sublattice black is white at the time on the GPU, because there's no interaction between 2 sublattices. And with another algorithm, which is basically invariant. Let's say for one simulation, for that simulation, you need to specify a temperature. Now we can simulate the system at different temperatures simultaneously at the same time. the spin configuration of different systems of those parallel tempering ability. It's called replicate chains. So in implementation, it's just a simple inversely parallel we have. And so that's part. So how are we gonna implement this algorithm on CUDA? So we establish a thread mapping to map to the block of a CUDA. Let's say, so for each temperature, we have a lattice, right? Each temperature is a replica of the system, so it has a lattice. Each lattice, we're using one dimension as a block dimension, one dimension as the thread within this block, and all lattices can be updated in form instead of the number of spin numbers. Compose it using a checkbox, and we update in the sublattice A and B and C and D. Then reduce the iteration number from n by n to a constant number 4. So larger than the thread number in this case. And another dimension for the block is for different replicas. So we define a thread block of each system, a different block number for different replicas. So we can map our system onto a CUDA thread block structure because we have lattice structure and using lattice space envelope decomposition and investment parallel combined, so easy to establish such mapping. So barebone of our code would be look like this. So parallel split. One non-parallel split is defined as you try to flip every spin on the system. So as I illustrated in the previous graph, split n iteration is reduced by 4 iterations. Each iteration is actually update every sublattice A in every block 0 to 7 in this case. So 4 iterations update to update the whole lattice. The reason we call full time of this kernel is because in synchronization within a block, there is no synchronization across the block. So to do it across the block, you can use this kernel function call. Then after a call to the sublattice 1, all the data, all the spins on that sublattice will be synchronized. Then you can call sublattice 2 and 3 and 4. In this way, you can synchronize all the data on the sublattice. Each kernel, you do the similar update scheme depends on different sites. Here, within global memory, you load the whole lattice into the global memory, and you determine which iteration you are, which 1 to 4 iteration you are. You update different sites. So site is a spin on the sublattice. Of course, the site ID is calculated according to your thread ID, according to your block ID X. Block ID is the dimension within a lattice, and block ID Y is the dimension for different replicas. That is spin number. So every thread executes same same scheme, same algorithm. It just act on different actually global memory size. So obviously there's some optimization we can do on this code. We will do all measurement on device. When we measurement, we want to calculate the energy or magnetization. Basically, magnetization or energy are defined as a summation of all the spins. So now you see where the reduction comes from. So we want to do a reduction across this system. Magnetization and calculate energy of this. And we want to swap different reference system on device. And you see the most expensive calculation for this model is just calculate the Boltzmann factor, potential something is the probability. Because the discrete model, the possibility for this number is actually limited, which means you can build a lookup table on the memory. The cost memory is an order of magnitude faster than the global memory, and the shared memory is an order of magnitude faster than the constant memory. So we also want to use a shared memory. It gives the freedom of the programmer to use this shared memory as a cache. How are you going to use it? So it will not handle this cache mechanism for you. So you want to use the shared memory efficiently. For example, we can actually chunk of this matrix and define a larger checkboard. Basically, it contains larger tiles. If you zoom out, it's actually another checkboard, and this big red tile, you can define it as a thread block, which means you can load this red tile, the spin of this red tile, load global memory to share memory one. Once you load memory, not go spin update within this red tile. So the way you use share memory as a cache, which the performance of is a little bit old, and the fastest GPU is on GTX 200, and compare with the very old cluster on our university computing center. So let's see, for a system size 400 by 400, it on an IBM cluster, it's going to run about 10 days. So 200 over 10 days to get the result. While you use a single GPU card for by 400 size, you can 1 day. So why we want to use GPU computation for this model. There are a lot of lattice model actually in science applications. You might want to try to use advantage of this GPU computing power. So, okay, second case study is about lattice model, which is also common. Like we have a water cluster, and this model we can do a space decomposition because the equation is local, it's range. While for a lot of range of scientific models, the equation is long range, which means there's an easy way to do space decomposition, and it's not on lattice, it's a water cluster. You can float everywhere. So we have this water model. Basically, it's based on Coulomb potential. Previous what we use is a simulation algorithm called Manchoplic. Somewhere this Manchoplic algorithm is ranked one of top 10 algorithms in 20th century among the cluster transfer, which I guess not familiar. So this Manchoplic algorithm is very popular in statistics, in statistical physics. It's based on your distribution you desire. You can collect the sample, simulate the sample in your color simulation, and generate the sample you want. This is the Boltzmann distribution, which is another ensemble distribution, which is given by this exponential thing. The distribution looks like it's a bell shape. And in a reader, there's a new algorithm called Wanda method. Basically, it does limit the energy distribution to a bell shape. Basically, if you have a bell shape distribution, it's centered with the energy, and the spread is very narrow, so you can easily get trapped with that distribution. For method, you have your energy is flat. Means every energy has equal probability, which means it's a random walk in energy. So the implementation just similar to the replica exchange. It's like inverse scheme of CUDA device. Now you actually multiple CUDA device. Since every sampling is random walk of energy within an energy space, let's say walk 1, 2, 3, it's a random walk within this energy space. Each thread can be a replica of your system, and you have as many threads as you can within a card, and using multiple cards across, and every certain steps you synchronize this data, and every another step is synchronized across all the GPU cards. So the simulation using Wanda method on GPU card. This is a result for simulation for a water with 50 water cluster. You may think this water cluster size is small, but actually, to my knowledge, this is the largest water cluster simulated for the ground state, not for the at higher temperatures, for the ground state, because it's very difficult to search. That's a global minimization problem related with energy harm. So, you're learning the last the Jesus one is the energy or the upgrade of the so which part of calculation are actually done on GPU? So for both cases, I model or this water class model, all the calculations are done on GPU. So then I don't use GPU as an accelerator. Basically, initially, memory copy all the data from host to the GPU, and all the calculation on this GPU, including and everything. Yeah, not the GPU itself. Yeah. Basically, it's used as a synchronization point. So across the block, you have the current function is looking for across different. Yes, across different GPUs, right? And at that time, and then for this code, there's no GPU direct. So we have to, let's say GPU 1 want to communicate with GPU 2, we have to transfer the data from GPU1 to the CPU1, and then let CPU1 do the MPI code. And the GPU direct, yeah, you can do the direct communication. Found the best optimization. For this second code, there's no mapping of your thread block onto the so you can try different block size, different block configuration. You can use the occupancy calculator provided by CUDA to calculate the best occupancy. You will do a simple run to test which grid block configuration will have the best performance on your specific card. So we have a comparable number of grid and block size give you the performance on this Fermi-based card. You need also to fine-tune how you do the synchronize on the CPU when you on the GPU card. Because from the end point of view, the more you do the synchronization, it converges faster. The cost cost time to do this synchronization. So what's the number of Monte Carlo steps you want to do synchronize across this GPU card? There's a trade-off between this synchronization overhead with your overall algorithm convergence. So every let's say 100 or 400 Monte Carlo steps, we do a synchronization across all the genres or model. Embarrassing parallel implementation of algorithms on these multiple GPU cards. So you can expect that we have a nice scaling when you increase the number of GPU cards. So one thing to notice is that this TX or Tesla S1070, they are both GPU architecture, and this latest are not related. Now latest card. This latest is the 2015. It's a Fermi card. You can see we expect about 2 times speed up when you to Fermi card from 100 architecture. So to talk, I show that the IP model is on lattice, is and for this type of model, what are results are reported in late literature. We have 50 or over 100 CPU. And that's what we expected for the lattice model on GPU applications. So this type of model are very suitable for CUDA programming. That's more really model for bioscience or material science. They have a model that they are not on lattice, and the interaction range is small, so the space decomposition is not that effective. But we can invert the scheme or some powerful algorithm and add GPU to it. A nice scaling. You can just multiple GPU, and we can just simulate a very complex system in GPU. Yeah. So, Tom, thank you. Right now. Yes. Yeah. So, you mentioned the long range like yeah. So, um, so doing those for uh, also use people which is not like say something um, because those systems are not back to you talk like you said, you have all the data wrong to you do everything. Right. So we have some comments to that. Okay. So it's about the long-range interaction on GPU. So yes, there's some advanced implementation for paper summation, like for CUDA potential, for that. For NAMD, yes, this already all for length. This code on the GPU, right? And they saw good performance on GPU. And there is technique to do long-range interaction on GPU efficiently. But yeah, that's so right now developing so you yes.